We are searching for a mathematical structure that dictates exactly where prime numbers occur. The objective is to build a deterministic model that calculates local prime density directly, bypassing the need for brute force trial division. The starting point for this analysis is the Chebyshev function, denoted as psi of x. By subtracting x from this function, we isolate the residual, the remaining mathematical noise after accounting for the expected baseline growth of prime numbers. This is a 2D coordinate space mapping, that residual. To analyze the frequency components hidden in this data, we transform the standard integer x-axis into a logarithmic scale, where t equals log x. The jagged residual signal is then interpolated onto a new, uniform t-grid. The working hypothesis is that once transformed into this log-scale space, the apparent noise contains an underlying structure, specifically a stable, low-frequency oscillatory wave. The core claim we are testing is that the phase of this extracted wave acts as a driving signal, directly modulating the density of prime numbers across defined, multiplicative intervals. We evaluate a specific forward window, taking the actual prime count, p, subtracting expected count, e, and normalizing by the square root of e. We convert this into a binary target. Any interval exceeding the train-derived median is classified as a positive event. The final benchmark for any proposed model is a stringent autoregressive mean reversion baseline. If the prime phase hypothesis is mathematically valid, correlating with current density is insufficient. It must predict the actual sign changes of future density at a rate higher than the raw inertia of the data itself. Every test requires a strict time-ordered split, 70% training data, 30%. Finally, a Hilbert transform extracts a continuous phase coordinate, theta, from the wave. In distributed computational research, stateless workers often inadvertently shift parameters across iterations. Minor changes in filter boundaries or interpolation methods can completely alter the resulting signal. We implement a cryptographic fingerprint lock to prevent this drift. Every intermediate state, from the bandpass output to the final phase coordinate, is verified against a master SHA-1 hash before the experiment can proceed. Unless the underlying signal pipeline is cryptographically immutable, any observed statistical effect is meaningless. Without strict controls, extracting phase is indistinguishable from curve fitting to noise. Initial testing produced highly compelling results. A model using these phase coordinates to gate prime probability generated strong out-of-sample predictions, reaching an area under the curve of approximately 0.743. To understand the mechanics of this predictive power, researchers analyzed the log grid residual to extract its dominant spectral peaks. This table shows the extracted frequencies. The top estimated gamma appeared at exactly 14.033, closely aligning with the first known Riemann Zeta zero. Early statistical tests compared the distance between these extracted peaks and known zeta zeros against a control group of random frequencies, resulting in a tiny p-value that suggested a mathematical link. However, the control group was structurally flawed. The random frequencies generated for the baseline mapped to gammas far outside the range of actual extracted peaks, artificially inflating the distances and completely invalidating the p-value. This chart shows the corrected experimental design. By enforcing a range-matched gamma permutation control, the null hypothesis samples random frequencies strictly within the exact same boundaries as the real extracted peaks. Under proper constraints, the statistical significance vanishes entirely, yielding a p-value of 0.62. The apparent coupling to Riemann zeta zeros was an illusion. The tight alignment was purely a structural artifact of the data's power spectrum and zero density. There is no unique, phase-driven relationship at play here. The final test for the prime phase hypothesis requires predicting out-of-sample residual changes against a strict time series benchmark. We evaluate the model using a phase transport metric, calculated as the change in theta over a specific forward horizon of 25 samples. This analysis scrutinizes candidates for structural relevance, including the geometric constant tau and the empirical frequency of 125 samples. The benchmark to beat is an aggressive autoregressive model incorporating 40 distinct historical mags, known as AR40. This chart shows the receiver operating characteristic curves for both models. The performance is nearly identical. The baseline AR40 achieves an AUC of 0.7601, while the full model adding phase transport scores 0.7613. The latent phase data provides a marginal lift of just 0.00118. We apply one final safeguard, an autocorrelation preserving circular shift null hypothesis, designed to test if a lift this microscopic holds any actual mathematical weight. When subjected to this strict null, the marginal advantage of phase transport fails to reach statistical significance. Forced to compete against robust time series baselines, the predictive illusion of phase transport collapses. Simple mean reversion, rather than hidden spectral phases, serves as the true mechanical driver. The log space oscillatory mode definitively exists within the filtered bandpass structure, but it provides no out-of-sample causal predictive power beyond the basic inertia of the prime data. Expanding the horizon to 100 samples reveals further degradation. At longer horizons, incorporating phase transport actively harms the model's accuracy. We must also reject the concept of privileged commensurability constants. When tested with rigorous permutation controls, the specific candidates of tau and 125 fail to demonstrate structural relevance. In time series classification, failing to implement autocorrelation preserving nulls allows label stickiness to masquerade as a newly discovered deterministic law. The prime phase lock hypothesis serves as a cautionary tale, a compelling mirage constructed from overlapping data distributions, flawed control groups, and insufficient baseline testing. Preventing these false discoveries requires an absolute, unbreakable commitment to time-ordered train and test splits. Cryptographic fingerprinting must be mandatory in data science pipelines to stop the invisible hallucination of results caused by computational state drift. Anytime a spectral alignment claim is made in a computational setting, strictly range-matched controls are not optional, they are required. Complex latent state models cannot be evaluated in a vacuum. Aggressive autoregressive benchmarks like AR40 serve as the minimum required starting point to validate any time series claim. The mathematical reality remains intact. Prime distribution at scale is stubbornly probabilistic in its local variations. It is highly resistant to simple harmonic gating. True computational rigor involves designing uncompromising pipelines and aggressive null hypotheses, engineered specifically to destroy our own conclusions.